In this video, we'll get a quick introduction to Markov chain Monte Carlo, or MCMC, simulation techniques. Let's first consider why we should care. During this course, we've been studying nice Bayesian models. Mainly, we've been able to identify a posterior model from the prior model and likelihood function by chugging their formulas through Bayes' rule. But we'll soon move beyond fundamental Bayesian models and onto models with multiple parameters in more complex settings. For example, we might be interested in a regression model of y, where this regression model is defined by multiple regression coefficients, theta 1, theta 2, up to theta k. We can apply the Bayesian philosophy in these more advanced settings, but it gets complicated. In more simple settings, we've been able to utilize the proportionality here, or to identify the posterior from the product of the prior and likelihood alone. However, in more complex settings, the posterior can be too complicated to identify from this product. For example, this product won't be the kernel of a simple beta or gamma model. In such cases, specifying the posterior requires that we actually calculate this normalizing constant in the denominator of Bayes' rule. That is, that we calculate the overall plausibility of observing data y across all possible parameter values. Yet this calculation also gets complicated in more complex settings. To calculate the overall plausibility of observing data y across all possible parameter values, we have to integrate across all of these possible parameter values. That is, we have to do this complicated multivariate integral. Actually doing this calculation can be prohibitively difficult, if not impossible. Yet, there's hope. It's true that in Bayesian modeling, we can't always specify or know the posterior model. But when we can't know something, we can approximate it. To this end, we'll use Markov chain Monte Carlo, or MCMC techniques, to approximate Bayesian posterior models that are otherwise too complicated to specify mathematically. The basic idea is this. We first simulate a sample of theta values, or set of theta values, theta 1, theta 2, on up to theta n, where big N is our MCMC sample size, or chain length. We then use this sample to approximate features of the posterior PDF, f of theta given y. It turns out that this step 2 will be straightforward. The bigger challenge is in step 1, actually simulating the sample of theta values. There are various approaches to this task. We'll start with the Monte Carlo approach, which is a special case of Markov chain Monte Carlo. Monte Carlo techniques have a bit of a dubious history. They were developed in the 1940s to better understand neutron travel for the nuclear weapons project at the Los Alamos National Laboratory. Monte Carlo was the code name for this top-secret work, a choice said to be inspired by the opulent Monte Carlo casino in the French Riviera. In terms of our goal of simulating a posterior model, Monte Carlo methods produce a random sample of size n from the posterior PDF, f of theta given y. Specifically, in this sample of theta 1, theta 2, on up to theta n values, each theta value is independent of the others, and each theta value is drawn from the posterior PDF, f of theta given y. Consider an example. In the familiar beta binomial model, suppose we start with a beta 4/6 prior for pi, and we collect binomial data on 10 trials. Upon observing 8 successes in these 10 trials, our posterior model for pi is a beta 12/8. Now, for illustrative purposes, suppose we weren't familiar with the beta binomial model and weren't able to specify this posterior. In this case, we could use Monte Carlo methods to approximate the posterior. There are many approaches that will produce a Monte Carlo sample. Consider just one. First, after setting the random number seed for reproducibility, we can take a random sample of 100,000 pi values from the beta 4-6 prior model. Then, from each of these prior plausible values of pi, we can simulate a binomial data point from 10 trials with the corresponding probability of success pi. Using just the known prior and conditional model for the data, these first two steps produce 100,000 pairs of pi values and data points y. To approximate the posterior model that balances the prior with the observed outcome of y equals 8 successes in 10 trials, we want to narrow in on just those pairs that have a matching data point, y equals 8. In this case, only 3,729 of the 100,000 simulated pairs had data points matching y equals 8. Thus, this technique produced a Monte Carlo sample of 3,729 pi values, the first three of which are shown here. Finally, we can use this Monte Carlo sample to approximate the posterior. For example, the distribution of our Monte Carlo pi values provides an approximation of the posterior PDF. That approximation is shown here. When we compare this approximation to the actual beta 12-8 posterior that we are trying to approximate, the results are nearly indistinguishable. Now, it's important to remember that the major point of Monte Carlo in practice is to approximate something that we don't actually know. Thus, we don't usually have this benefit of being able to check the quality of the approximation, as we've done here. That said, our success in this example provides some peace of mind that Monte Carlo approximation can actually work. Now, this is all great. The Monte Carlo sample is nice and random, and we've seen that it can provide a close approximation of our posterior. But remember that the whole motivation for this conversation is that we only need approximation tools when the posterior is really complicated. And when the posterior is really complicated, we typically can't directly sample from it, as we did in our Monte Carlo example. And that means when we can't sample directly from the posterior, we can't implement this Monte Carlo method. This is where Markov chain Monte Carlo comes in. MCMC methods can scale up for more sophisticated Bayesian models. Like Monte Carlo, MCMC methods produce a sample of parameter values. Yet a Markov chain grows one value at a time, from theta 1 to theta 2 to theta 3, on up to theta n, where again capital N is the chain length. Each value in the chain here is drawn from a model that depends upon the previous value. For example, theta I plus 1 is drawn from a model with PDF G that depends upon data y and the previous chain value theta I. This evokes the chain terminology. Each chain value depends upon the previous value in the chain, which depends upon the previous value, and so on. This chain of dependence also satisfies the Markov property. That is, given the present chain value, theta I, the future value, theta I plus 1, is independent of all other past values. Or, in mathematical notation, if you tell me all of the past chain values, theta 1, on up to theta I, the model of the next value, theta I plus 1, depends only upon the previous value, theta I. To build some intuition, consider a Markov chain for a beta 12-8 posterior. Let's start with a short chain or sample of just 20 pi values. As it grows in length, this chain traverses the sample space of possible pi values, that sample space being on the y-axis here. Each step or iteration of the chain depends upon the previous step. Thus, you'll notice here that sometimes the chain trends upward or downward before correcting its path. Further, notice that in just the first 20 iterations, the chain here largely explores values of pi between roughly 0.45 and 0.8. After 200 iterations, the Markov chain has started to explore new territory. The hope here is that by the end of the simulation, the chain will have visited various pi values with a frequency and range that's reflective of the posterior model. But you might be a bit skeptical here. MCMC methods can scale up for more sophisticated Bayesian models, but there's a cost. First, remember that the chain values are dependent, each value in the chain depending upon the previous value through the conditional PDF G. Not only that, but this PDF G from which we draw the chain values is not the posterior PDF F. As such, a Markov chain, theta 1 out to theta n, is not a random sample from the posterior. This might all seem strange, that we're trying to approximate the posterior model using a dependent sample from something other than the posterior. But when done efficiently, and when the chain is long enough, this strange dependent Markov chain will at least mimic or behave like a random sample from the posterior. As such, the distribution of a Markov chain sample will converge to and provide a good approximation of the posterior. For example, check out our final Markov chain simulation of 10,000 pi values for a beta binomial model. This chain provides an excellent approximation of the beta 12.8 posterior, despite the fact that none of the chain values were actually drawn from this posterior model. In short, by math magic, Markov chain Monte Carlo techniques can help us approximate posterior models that are otherwise too complicated to specify mathematically.